Don't do anything too precious. Good. Are we rolling?
Yeah. Okay.
You're supposed to.
The Wi-Fi came off.
All right. So, right. So point one is that attack has to occur perpendicular to the plane of the molecule. Now, what this will mean, and we'll get to the carbonyls in more detail later on, but what this will mean is attacking carbonyl compounds is really going to be easy because the carbonyl carbon is going to be very delta positive. Right? That's a combination of not just the inductive effect of the O, but also of the resonance effect in the carbonyl. So I can draw a resonance form with a plus charge on that carbon. So the combination of induction and resonance makes the carbonyl carbon very, very delta positive. So that makes it a really good electrophile. That's point one. Point two, it is sterically open. Because unlike the SN2 reactions, for example, where the nucleophile has to approach this site, where these groups are folding back in the direction of its approach, I have no such difficulty attacking a carbonyl. So not only is the carbon very positive, combination of induction and resonance, but it is sterically open. I'm attacking from here, whereas my groups are in these positions. Agreed? Of course, the other factor is, should I attack it, the bond I break is a pi bond, and pi bonds are labile to begin with. All right. So BH4 minus and ALH4 minus are similar. They both are tetrahedral with a negative charge on the metalloid or the metal. So this is the anion of LaH, just as the lithium plus that's associated with it. This is the anion of sodium borohydride. It has an Na plus associated with it. You can well imagine having a negative charge on a metalloid, or God forbid, a metal, must be uncomfortable. So what these species are really good at doing is getting rid of H minus. Right? So the way they tend to react is by getting rid of H minus. That with because metals normally are electron releasing groups. Metals tend to form cations. These are very highly energetic. They spit out H minus very easily. So we call them hydride donors. We call them hydride donors. Okay? So the way this reaction happens is, let's call it MHH3 minus, where M is either boron or aluminum. What this species does is it attacks the carbonyl, the pi bond breaks. We generate, I don't care about the metal species, we're not concerned with the inorganic things. We generate this species, which is the alkoxide. So the first H comes on as H minus, literally as hydride. From here, we have water. Either the water is in the system when we're using sodium borohydride aqueous, or we add it in the second step. The alkoxide attacks water, that's an equilibrium. We generate then our product, which is the corresponding alcohol. So these are two-step reactions, right? In step one, H minus comes on. In step two, functionally, H plus comes on. Okay. If the carbonyl compound has two different groups on it, let's say it has, it's H and methyl, or it could be methyl and ethyl, it doesn't really matter. If it has two different groups on it, what's going to happen is the following. Now it's flat, so it's achiral. All flat things are achiral. When the hydride attacks, it gives rise. Okay, so let's make this D. Okay, so when the hydride attacks, what I'll have is that species. This is now a stereocenter. Okay, it remains a stereocenter when the O gets protonated. So this is first, second, well, let's work if I put my eye, if I put my eye here, and I look this way, this is first, second, third. So first, second, third, so this is R. Right? R compound. Or if you want, I could interchange groups. That might be easier. So if I interchange H and D, let's do that. If I interchange H and D, so I'll have D here and H. If I read this, it's first, second, third, which looks R. Oh, it's actually, which looks R, but it really is S. Actually, that's the S compound. How did that work out? So this is first, second. Oh no, actually is S. Yeah. So this is the S compound, right? So let me do it again. So if I put my eye here, which looks diseased, but that's all right. If I put my eye here, I'll have OH methyl D, which this way, wait a minute, so OH methyl D, right, so that's S. And if I swap this pair of groups, so I have 1, 2, 3, that looks as if I'm going R, but since I swap the groups, this really is the S compound. Did we get that? Yeah? Good. All right, so
Dr. Donovan.
Go ahead.
D and C, so T has priority over D.
And D over
has
H.
priority over H.
Yeah. So the way you do priorities is really by atomic number first, and then if they have the same atomic number, so the isotopes, then by atomic mass. Okay, so in other words, if I do the top attack, I make the S enantiomer. We know that cannot be the end of the story, because achiral starting materials, or optically inactive starting materials more correctly, cannot generate optically active product. The carbonyl compound, because it's planar, is optically inactive. This species has no stereocenter. The species is not chiral either. Therefore, I have two optically inactive compounds. They cannot give me an optically active product. How do I fix that? Right. The attack can occur from the bottom. So if we get attack from the bottom, and I'm going to write it out. Yeah, I'll write it here. If we get attack from the bottom, what we will get instead, so we'd have carbonyl, DH, attack from the bottom will give rise to this species, so H, O minus, D, did I have an H there? Oh, good lord. That's methyl. And then when I protonate that species, what I'll get is this one. So OH, H, methyl, and D. And if I read this, it's the same thing. You know what? I'm gonna take this one and let's see what's an easy way of doing it. I can turn it, I guess. So if I turn this, yeah, I'll just tumble it about this bond. So what I'll have is, if I put the H here and I put the OH, so I'm just going to turn about the bond. So I'm going to bring the H in the plane of the board on top. Where does the D end up? In front of the board. And the methyl is behind. So these two things do not superpose. So the H and the OH match, but not the D and the methyl. Agreed? So these two are enantiomers. So when I attack a carbonyl compound by, say, the hydride transfer agents, what I will generate is a racemic mixture of products. Okay? I'll get a racemic mixture of products. Okay. I can do this reaction another way. So
You're saying the bottom attack and the top attack are enantiomers?
no. So the bottom attack and the top attack lead to two different enantiomers. But
Right.
since both will occur in equal amounts, what I get is a racemic mixture, right? Because attack at the bottom and attack at the top are equally facile.
So that compound there is an enantiomer, the bottom one.
Correct.
Right there,
Yes.
across that.
Yes. So these two are enantiomers. So I can reduce the carbonyl compounds using so I'm going to say 3A is via hydride donors. But in reality, all I'm doing is I'm adding H2 across the double bond. There is another very easy way of doing that. I'm going to be a little bit lazy here. There's another easy way of doing that, which is use hydrogen gas and a catalyst. So if I use hydrogen gas and a catalyst, the hydrogen molecule, if you remember, will bind to the catalyst surface. The flat carbonyl compound will simply come and sit down like this, and I get the OHs on the same side, the H and the OH on the same side. Or it can sit like that. Agreed? If it adds this way, I'll get one enantiomer. If it adds this way, I'll get the other enantiomer, and I'll get both. So I can literally do this reaction, B, with hydrogen gas and a catalyst. So typically platinum or palladium, any one of those things will work. So if I treat a carbonyl compound with hydrogen gas and a catalyst, what I'll end up with is the corresponding alcohol.
So reaction A had the metal one, and reaction B had the...
Yes. So reactions A are via hydride transfer. So that's with the lithium aluminum hydride followed by water, or the borohydride followed by water. The B reactions are just hydrogen gas and an appropriate catalyst. And there's a list of catalysts. Typically platinum, palladium, nickel, and so on will do that reaction. Okay, so that's a reduction of a carbonyl. And that's the aldehyde. That's the aldehyde. I can do another preparation of the alcohol, because remember we said, if you look at the oxidation tree, for the primary alcohol, above the aldehyde was the carboxylic acid. So I can say 4 by reduction of carboxylic acids. So if I take acetic acid and I treat that with LaH followed by water, what I generate is the corresponding alcohol. So I can reduce a carboxylic acid through the aldehyde all the way down to the carboxylic acid. I'm sorry, all the way down to the primary alcohol. I can't reduce an acid into a secondary alcohol because acids don't live above the secondary alcohols. The tree is very specific. Primary alcohol to aldehyde, aldehyde to acid. Okay? So I can reduce carboxylic acids. This is a 4 electron gain down to the alcohol. You would notice the reagent I use is LaH. Sodium borohydride does not work. And that's one of the specificities we're going to have to learn. Right, one more. I can take a carboxylic acid and I can reduce it with a derivative of lithium aluminum hydride. So lithium aluminum hydride, if you remember, the aluminum hydride part is the active part. That looks like this. There is a version of this species which looks like this. And this is called lithium aluminum tris T-butoxy hydride. So you have the lithium cation associated with the anion. So it's lithium aluminum. I have 3 T-butoxy groups. So it's tris T-butoxy hydride. That reagent acts on carboxylic acids, but it doesn't reduce it all the way down to the alcohol. It stops at the aldehyde level. And I'll tell you why in a second. So if I use lithium aluminum tris T-butoxy hydride followed by water, what that would generate is the corresponding aldehyde. That's an H. I can then take the aldehyde, reduce it with either LaH followed by water into the alcohol, or I can use aqueous sodium borohydride to make the alcohol. Either one of those would work. So there are two questions to ask and answer. Give you guys a second to catch up. So question one is, why on earth would I use the second pathway if lithium aluminum hydride could get me there in one step? If I have a carboxylic acid and my intent is to make the alcohol, I can just use LaH followed by water and I'm into the alcohol. What is the value of converting the acid to the aldehyde and then the aldehyde to the alcohol? And the answer is labeling. So, for example, if I wanted to convert this carboxylic acid, if I want to convert acetic acid into ethanol, I could easily use LaH followed by water. Not a problem. If I want to convert it into this alcohol, I would use LAD, lithium aluminum deuteride, followed by water. Not a problem. But suppose I want to convert it into chiral ethanol, D and H, right? Or D and T, or whatever. How do I do that? Because the problem is using LaH or LAD puts on both H's or both D's or both T's, whatever. So here's what I would do. I would take this and use lithium aluminum tris T-butoxy hydride, for example. That will convert the carboxylic acid into the aldehyde. And then I can use LAD followed by H2O, or I can use sodium borodeuteride, right, in D2O. And that's going to give me my product.
The reagent up there for the top arrow one?
Here?
Yeah.
Right, so this way.
Oh, to get to it.
Yeah, so there's no single reagent that will do this. What you do is, in other words, what we're doing is, we are sequentially adding on sequentially adding on H's. We put an H first and then a D, or a D first and then an H. It doesn't really matter.
That's like the achiral compound.
Right, correct. And of course, at this point, what you're going to end up with is the plus-minus mixture, because you're going to get attack in the front and attack in the back. So let me give you a scenario where this is relevant. So suppose I give you, if I give you, let's see, if I give you this compound, yeah, suppose I give you this compound, and I ask you to convert that one into that one. or even into this one, which is kind of the same idea too. Say T. Let's make it CL. So we do both. Okay, I'll do this one first. So what are the conspicuous things we notice about this reaction? What's perhaps the most conspicuous thing we notice in this reaction?
Different labels.
Say again? We've lost a carbon, right? That's a C3 species, that's a C2 species. If we've lost carbon, what is indicated? Ozonolysis, and therefore an alkene. Very good. So what I'm going to do is I'm going to convert this compound. Okay, I'm going to come back to this one. Do we have this piece? Do we have all of this? Yes? Yes. So what I'll do is I'm going to convert this compound into an alkene. Then I'm going to ozonolyze to make the carboxylic acid. This carboxylic acid has no H's. On this carbon, there are no H's. So understand, here I had two H's, right? So here I have two H's. When I make the alkene, this carbon now has one H. When I make the carboxylic acid, that carbon now has no H's, right? So this carbon is this carbon is this carbon. That's the carbon in my product. So for me to convert this carbon with two H's to a carbon with a D and a T, I have to remove both H's. And if I convert this to the carboxylic acid, both H's are gone. And then I can at will add whatever H or D or T I want on. So I would treat this first with, doesn't matter, I can use either lithium aluminum tris-T-butoxy tritiide, right, followed by water, and that's going to give me the aldehyde with T. And then I can treat it with sodium borodeuteride in water, D2O, and that's going to give me my product. Or I could have used lithium aluminum tris-butoxy deuteride followed by sodium borotritiide. Agreed? Now I'm going to get the plus, so that's going to get me the OH. And then to get my final product, I use PCl3 or something. And that's going to give me my, my products, my plus minus mixture. So DTCl, plus minus. Right? This is a really good trick. If you have two H's and you want to clean the board and put on D's and T's, the best way of doing that is to oxidize that carbon to carboxylic acid. At that point, you have no H's, and I can sequentially put on H, T, D, whatever I want.
Is that NABD4 and
Yes.
D2O?
Yeah. Okay. Right. So that's the value of doing it this way. There is a second point which needs to be addressed. Let's say I started off with, propanol, so methyl ethyl. Well, I'll tell you what, I'll leave that to do carbonates. Let's leave that alone. Okay. So this is 4? Right. 5, which is the last, 5 is the last one we, 5 is the last one we do. 5 is the last one we, yeah, 5 is the last one. So 5 is by treatment of aldehydes and ketones with organometallic compounds. Metallic compounds? You guys have met organometallic compounds, yes?
I mean, it's just basically like something like that.
Yeah,
It's
they're
just
virtually identical to this, yes?
boron, yeah.
On the over there, what are the reagents
Oh, yes, I didn't put those in. So this is an elimination. So I just need I need a strong base. Normally when I do elimination, I have to ask, is it Satzev or anti-Satzev? In this case, it doesn't matter, right? So I can use 3 molar methoxide in methanol and heat. And then this would be ozone, and I would prefer to use hydrogen peroxide. That way the extra carbon just bubbles off as carbon dioxide. And then, you know, now, again, so here, I could have done the lithium aluminum tris-butoxy deuteride, and then this would have to be the sodium boron tritiide, right?
So, you had another reaction up there at first that we were gonna go over, and we didn't. Right?
Oh shoot, yes, maybe I did have another one.
Okay. But it would go the same way.
It would the same way. Although, yeah, we'll come back to that one.
The zinc one?
Yeah, there was one that was C3 to C3, right? But we didn't use carbon. Okay, and the reason I'm going to push that one back a little bit is because what will be inherent in the reaction is, okay, let me just explain. So if I have this compound and I want to convert that into this one, so remember we said that all syntheses hang on a set of axes that are going to involve functional group heater conversion, carbon-carbon bond formation and breakage, and redox. Just a cursory examination of this tells me I'm using 2 of those. Which 2? Functional group heater conversion, because I'm going from a chlorine to an oxygen. So I've done what really is going to be an SN reaction to convert this thing into an oxygen-bearing species. In other words, I'm converting this into an alcohol. What else do I do? Oxidation. I'm at the alcohol level, that's at the acid level. Right? So what would be inherent is oxidizing the species into here. And the reason I'm pushing it off is because we haven't done those reagents yet. But what I would do next in that question is, once I make that, all I have to do now is go ahead and reduce it down to the aldehyde, put on T, reduce it down to the alcohol, put on D, so I'll have this, and then I can convert that with PCl3 in, so I'll have this is TD, I'll put on PCl3 or whatever, some kind of crap like that, and I have D and T, and we're done. Right? So if the intent is to obliterate these H's and change them into D and T, so in order to remove those and to replace them, the way to remove that is to convert it to the carboxylic acid. Right? And you can easily tell that involves converting CCl to CO. That's just cold aqueous hydroxide. For now, you don't know the reagent to do the oxidation. You will on Monday. And then once I'm here philosophically, that's lithium aluminum tris-butoxy tritiide, then sodium boron deuteride, and this PCl3, and we are done. Right? The only question mark here is that reagent. Okay? Okay. So and I can't stress enough, this is a good trick. Trick is such a bad word. You are bound to get one of these questions on one of your exams.
Can you go
Right?
over the reagents again for that reaction?
Right, so this would be aqueous hydroxide. It have to be cold because you don't want to get SN, you don't want to get E. And then, so you don't know this reagent. And here, this could either be lithium, aluminum, tris-butoxy tritiide, followed by water. And then this would be sodium borodeuteride in D2O, Or I can use LAD followed by H2O, and that'll get me here. And then it's just PCl3 or PCl5 or SOCl2, any of that lot. Right? Any one of those reagents would work. Right? So there's a now again, and remember now, so the way you guys do this question, the way you would do this is you don't write the reagents first. Right? You say, I've got to convert this to that, this to that, this to that, whatever. So you work out the species first. The cheat sheet will give you the reagents. Right? So once you've identified what I have to do, the sheet will tell you how to do it. The sheet will never tell you what to do. Right? That's where your training comes in. Okay? All right. So I just want to do one more thing, then we stop. Yeah. Are we done with this one? Okay, that's all right. So one last thing, and then we stop. So treatment of aldehydes and ketones with organometallics. This is virtually identical. I did erase it. This is virtually identical to what we had done with the hydride donors. If you recall, we said they had metal hydrides that would attack a carbonyl group, and it would attack from the top and from the bottom. We argued that this reaction was fairly facile because the metals would dump electron density onto the H, making it a really good hydride donor. It would attack, we'd have HO minus, and then this would simply pick up a proton from water, and we'd make our product. Right? This together with its enantiomer if these two things were different. Agreed? What this reaction does is it reduces the carbonyl compound without changing the number of carbons. So, if this was methyl and ethyl, methyl, ethyl, methyl, ethyl, right. And again, I'll get the enantiomer. This was a C4 compound making a C4 compound. C4 ketone to C4 alcohol. The number of carbons does not change. But organometallic compounds are MR. So whether it is an alkyl lithium, whether it is a Grignard reagent, whether it is an alkyl sodium, or whatever, these are MRs. And just as the H is full of electron density and comes off readily, so is the R. So I'm going to change my mechanism. I'm going to replace this by R. The reaction is identical. R attacks top and bottom, gives me an R group here, gives me an R group here. This alkoxide pulls up a proton from water, gives my alcohol. And I'll get the plus and minus compounds. The difference is, when I use the hydride donors, the number of carbons didn't change, which meant aldehyde with, let's say, sodium borohydride or whatever, that gives rise to RCH2OH. It makes an alcohol. That is not true in our case. The aldehyde, RC-OH, when I use, let's say, an alkyl lithium, that will, followed by water, that will generate a secondary alcohol. It really is a reduction because we're going from the aldehyde level to the alcohol level. But instead of using H minus, I'm using R minus. So I'm converting an aldehyde into a secondary alcohol. What would happen with a ketone? If I use a ketone with an organometallic, what would I get? I get a tertiary alcohol. These reactions are useful because they are ways of forming carbon-carbon bonds. And methods that make carbon-carbon bonds are relatively rare. Okay. Let's stop there. We'll pick up here on Monday. There are two other little issues we want to talk about, but let's stop.
And the R of H2 of the last reaction.
I'm sorry, say again?